This video is about CSMACA, which is the main method for medium access control in wireless LAN. In general, there are two so-called coordination functions, or you can also say basic possibilities how wireless LAN can work. The distributed coordination function is a decentralized approach where each station implements the algorithm and no station has a special role. It can be applied both for infrastructure networks and ad hoc networks. All stations compete with each other to get access to the medium. Even though the algorithm tries to avoid them, collisions can happen, and therefore there is no guarantee for successful communication. Each IEEE 802.11 station has to implement DCF. The point coordination function is a centralized method which only works in infrastructure networks. The point coordinator, which is actually the access point, controls the medium access during the contention-free period. This means that each other station is only allowed to send if the point coordinator has granted it the right to send. Because the point coordinator has the full control over the medium, collisions cannot happen, and it is possible to give guarantees for successful medium access. PCF is an optional method, and current products actually do not implement it. The basic idea to realize priorities is to define waiting times for medium access. The shorter the waiting time, which is named interframe space, the higher the priority. If it is allowed to use just the short interframe space SIFS, then the frame has the highest priority. This holds only for control frames or for a previously reserved medium. The next IFS is PIFS, which is used only in the context of the point coordination function. It will not be considered further in the video because the point coordination function is not actually used. DIFS has the lowest priority and is used for data frames. The actual times of the interframe spaces depend on the physical layer implementation. In the figure at the bottom we see two situations. At the beginning the medium has been idle. In this case, a station has to wait for the time DIFS and can then send a frame. If the medium is busy due to the transfer of a frame, then it is necessary to wait for DIFS plus a random waiting time. You can see this random waiting time indicated in the contention window. The reason for doing so is that it is assumed that there may be more than one station which waits for the medium to become free. If these stations just waited for DIFS, then there would be a collision. However, with DIFS plus a random waiting time, there are likely different waiting times. In such a case, a station with a longer waiting time notices that the medium is no longer free and does not start to send. In the figure, you also see that the times SIFS and PIFS are shorter. On the next slide, we have some general remarks on the CSMACA method. When you take a look at the abbreviation, you see that only the last letter differs to CSMACD. The CA at the end stands for collision avoidance instead of collision detection. The whole method is an adaptation of CSMACD to the different conditions in wireless networks, in particular the hidden terminal problem. This problem has a consequence that both carrier sense and collision detection do not work as reliable as in fixed networks. Nevertheless, you still use carrier sense, which means that the physical layer provides a clear channel assessment signal to indicate whether it observes a free medium. A station only sends on a free medium and in compliance with the waiting times as explained on the previous slide. An important difference to CSMACD is that the sender cannot detect on its own that it causes a collision. The detection that a collision has happened has to be based on collaboration with the receiver. The receiver has to confirm that it has received the frame. In wireless LAN, there is always a half-duplex situation. If a station sends data, then it cannot observe the medium anymore. Its antenna is used either for sending or for receiving. Parallel communication is hardly possible because the sent signals are much stronger than the received signals. As you know it already from CSMACD, CSMACA uses also a backoff algorithm for retries after collisions. Now I'm explaining you an example. By the way, you can find examples like this directly in the standard documents. Here we have the stations S1, S2, S3 and S4. The green arrow indicates there is an internal provisioning of a data unit towards the MAC layer. The station wants to send the frame and starts to assess the medium at this point. If you see data in the drawing, then this means that a station actually sends data onto the medium. If you find backoff elapsed and backoff remaining, then these are times which are relevant internally in the station. At the beginning, S1 wants to send a frame. Since the medium has been free before, S1 just has to wait for the time DRFS and can then send the frame. S2 also wants to send a frame and starts to wait for DRFS, but then it observes that the medium is in use due to the frame of S1 and it stops the attempt. Also S3 wants to send, but finds a busy medium. After the frame transmission of S1 ends, both S2 and S3 start to wait for DRFS plus a random waiting time. At this point, you see that the random waiting time makes sense, because there would be a collision otherwise. The time that S3 has chosen by random is shorter than the time of S2. So for S3, this backoff time completely elapses and then S3 starts to send a frame on the medium. At this point in time, S2 notices that the medium has become busy. It stops its attempt to transmit a frame, but freezes the remaining waiting time. This is a fairness mechanism, because in the next attempt, this remaining waiting time is a new waiting time for S2. In this way, it is more likely that S2 will have the shortest waiting time then. During the transfer of S3's frame, S4 has prepared a frame that it wants to send. After the end of S3's frame, S4 waits for DRFS plus a random waiting time. In this example, the time that S4 chooses by random is the same as the time for S2. As a consequence, both start to send at the same time. This is more inconvenient than in an Ethernet network, because S2 and S4 do not listen anymore and do not notice the collision. They both send the whole frames even though they collide all the time. The situation that you have seen at the end of the previous slide, but also the use of the 2.4 GHz band by other VLANs, Bluetooth microwave ovens, which leads to interference, makes it necessary to modify the procedure. It is useful to introduce acknowledgement frames for each unicast frame and to provide them with the highest priority. This means that after the transmission of a unicast frame, the next frame should be the acknowledgement frame by the receiver. Afterwards, the use of the medium can continue as before. Acknowledgement frames are not sent after broadcast frames. You can think about that on your own, why this doesn't make sense. There is an optional improvement of the basic procedure, which is called request to send and clear to send. A station that wants to send a frame can send an RTS frame first, which is quite short. The potential receiver of the frame can reply with a CTS frame. Both RTS and CTS contain a reservation time. Other stations take note of the reservation time in their network allocation vector, so they will not send own frames for the reservation time. With the RTS-CTS method, usually only the RTS or CTS frames may be destroyed by collisions, but not the much longer data frames. The longer the data frames are, the more efficient the method is. If the data frame is relatively short, then you can also try to send it directly. The use of RTS-CTS is optional, but each station has to understand it if it is used by another station. On this slide, we see how RTS-CTS works. S1 sends the RTS and S2 replies after SIFS with CTS. Then the data frame is sent, which is confirmed afterwards. For these steps, SIFS is used. Other stations take note of reservations in their internal network allocation vectors.